Welcome everyone to the first seminar of 2022 for the Centre of Research Excellence in the Prevention of Falls Injuries. My name's Charlotte McLennan. I'm a PhD candidate with the Institute for Musculoskeletal Health, funded by Sydney Local Health District under the skillful guidance of Kathy and others. So before we properly introduce Terry and our topic today, I'd just like to start by paying my respects to the traditional custodians of the land from which I'm presenting today. And for me, that's the lands of the Gadigal people of the Eora Nation. So I pay my respects to their elders past, present and emerging, and extend that respect to the traditional custodians of all the lands on which you're all coming from today and all the lands across Australia. So just a couple of announcements. There is a call for abstracts for the International Injury Prevention Conference, which will be held in Adelaide this year from the 27th to the 30th of November. So there's a great opportunity for falls and fractures to be on the agenda here where they haven't otherwise necessarily been at the forefront. The call for abstracts does close on the 20th of March. You can read more about it on the website. And I know Kathy is involved in this. So if you have any particular questions, I'm sure she won't mind me dropping her in as someone to approach. The other notification is a save the date for the 10th Fragility Fracture Network Global Congress, which is scheduled for the 20th to the 22nd of October in Melbourne this year. We're not actually aware of a call for abstracts being open yet, but anticipate that this will come up very soon. And so keep your eyes peeled. Okay. So moving on to our presentation for today. So we're very lucky to have Professor Terry Haines, who's a Chief Investigator on the CRE, with us today to present on the Stepped-Wedge Cluster-Randomised trial, enabling change while generating evidence. So Terry's the head of school at the School of Primary and Allied Healthcare at Monash University, and this follows his previous appointment as Director of Monash Health and Monash University Allied Health Research Unit at Monash Health. He's pursued work in the areas of falls prevention, implementation, and the translation of evidence in practice, so is in perfect stead to present on this topic to us today. So over to you, Terry. I'll stop sharing.
Thank you very much, Charlotte. And I'll just activate my share screen again. Just give me a nod if that's coming through now.
Yes, looks good.
Fantastic. Thanks very much. Okay, so today I'd like to share with you some of my thoughts about this stepped wedge design, which is a particular research approach which has been gaining in popularity in recent years. It's something that I've had a lot of involvement with stepped wedge trials and also the design of stepped wedge trials and how they can be adapted for different situations, which I'll cover a little bit more about later in the presentation. The stepped wedge design really comes as a bit of a hybrid style approach between something that generates high-level, robust research evidence while also trying to take into account the organisational imperatives that are often encountered and can be a barrier to conducting experimental research, particularly in the health services context. So I'd like to discuss some of these issues today. From a high level though, if we're thinking about falls prevention and why we might want to do a randomised trial of any nature, we often are confronted with the question of, does this intervention work? Essentially, that's what we want to find out. Does this intervention work? Does doing X cause Y? Now, randomised controlled trials are the gold standard. I've got the gold bars here because I think the first time I saw Stephen Ward do a presentation on research evidence, he used gold bars to describe the amount of evidence. So I'm trying to maintain that gold bar theme. But even with randomised controlled trials, we still need to be careful. There's still potential sources of bias, things that will distort the truth, things that will lead us to conclusions that may not be the true nature of the relationship between X and Y that we're investigating. I've listed on the slide here some of those things such as pre-trial issues, confounding or selection bias, misclassification of intervention that can happen during a trial, or after a trial, data collection has been completed, looking at things such as issues of missing data, selective reporting, or use of different outcome measurement approaches for different groups across the study. Now, sometimes we can't use a conventional randomised controlled trial approach. And when I say conventional randomised controlled trial, I'm talking about where we randomise individual people or patients to a control group or an intervention group. Now, some of the reasons are that people sometimes exist in natural groupings, and you're wanting to recruit people in those groupings into your trial. So this could be groupings such as classes, family groupings, general practices. In the sorts of falls prevention research I often conduct, it's hospital wards. People exist in hospital wards. And there's a whole lot of reasons why those people stick together. So in hospital-based falls prevention research, we often see, and we have research evidence supporting that there's different cultures for reporting falls, for example, that might exist and vary between different wards. There's different environments, there's different ward-based processes, and there's a whole range of background factors that group people in that ward together in some way. So they're not considered to be strictly independent of each other, which really is a requirement for entering into a randomised controlled trial. Other issues that might come up might relate to the intervention itself. It might be an intervention that draws together systems of care, models of care, and it's something which is very difficult if you're changing a whole model of care for a health service or a unit, a work unit within a health service, such as a ward, that you can't separate individuals on the same ward, one to receive one model of care and one to receive another. So sometimes it's the nature of the intervention that you're looking to test, which dictates you can't use a conventional RCT. A final barrier which I wanted to raise today is that some people just don't want to play this game. Some people don't want to be in a control group, and therefore will say, no, I'm just not willing to have your research conducted in our organisation unless everyone is getting the intervention. So there are some of the reasons I commonly encounter as to why a conventional randomised controlled trial is sometimes unable to be used to test the question of, does an intervention work? Now, cluster randomised controlled trials are a potential solution to some of these issues. They're very useful when it's preferable to allocate groups of individuals to an intervention or control condition. So if those groups are naturally existing when you recruit them, or if your intervention in particular is targeted at groups, naturally occurring groups of individuals rather than specific participants. Now, in some circumstances, it may be possible that both can be conducted, a conventional randomised controlled trial and a cluster randomised controlled trial, and that it is possible that a cluster randomised controlled trial in some circumstances may in fact be superior for testing the question of, does this intervention impact this outcome? I remember when writing my PhD thesis, at the time there was some great controversy about the role of hip protectors for the prevention of falls and fractures in residential aged care facility residents. I remember at the time of writing my thesis that there were some early randomised or some early cluster randomised controlled trials that found in favour of hip protectors for reducing hip fractures in nursing homes. However, later individually randomised, conventional randomised controlled trials found no effect, which made me question, well, is it that, was there some difference in the hip protectors being used, or was it something to do with the research designs being applied? And when you think about the research designs of the cluster RCT versus the individual patient conventional RCT, we have to think, is there a hierarchy that we believe applies? So is the conventional RCT going to give us more gold standard evidence than the cluster randomised controlled trial? And there have been some who have argued this case. And if we apply that to this particular context, if we say that the cluster randomized controlled trial is lower in the evidence hierarchy, do we have to interpret these findings as saying that hip protectors had no effect? Well, I thought about the context of this area to some degree, and I felt that possibly you could construct an argument that the cluster randomized controlled trial is actually better, because in this circumstance, it would allow nursing facility staff to consistently encourage all residents to wear their hip protectors, possibly leading to higher levels of compliance and subsequent to that demonstrated efficacy than an individually randomized controlled trial, possibly where the staff aren't too sure. Is this a person in the intervention group? Is this a person in the control group? I'm not sure whether I should be encouraging this resident to be wearing their hip protectors, leading to lower compliance rates with use of the hip protectors. So I can see arguments that can be validly constructed that cluster RCTs in some circumstances may actually provide evidence that is more reflective of what you would encounter in real life situations than an individually randomized controlled trial. Now, I'm just going to introduce some diagrammatic terminology that I'll use in the remainder of this presentation. This is how I demonstrate or visually represent a cluster randomized controlled trial. Here in this diagram, I have boxes that indicate clusters and a particular time period. The S indicates a subject when they enter the trial. The arrowhead indicates when we've got collection of an outcome measure. The grey shading represents an intervention group condition, and white indicates a control condition. So here we've got 4 clusters in total, each with 2 subjects in each cluster, although I could use yes to represent multiple subjects, and an outcome measure is being collected on each subject in each cluster. Now, for cluster randomized controlled trials, there's a couple of different varieties. On the bottom left-hand side, we see the simultaneous recruitment and commencement of the cluster randomized controlled trials, and each with 5 time periods. So this is something that you might get, say, for example, if over a 5-year period, you recruited all of the students in a grade 1 class at a particular primary school. So maybe the primary school has 4 grade 1 classes, and each grade 1 class is randomly allocated to being intervention or control, and that over 5 successive years, you recruit those same classes, and each year the children provide an outcome measure. It might be a particular test score for mathematics at the end of the year. So that's how I represent that style of cluster randomized controlled trial. On the right-hand side, we have a staggered commencement of cluster randomized controlled trial, whereby we have 2 classes in the first year, but then the second year we have 4 classes until the final year where the first 2 classes are no longer contributing data. So with a cluster randomized controlled trial, you can have staggered commencement. You don't have to commence every cluster at exactly the same time. Now, this is important because this is an important difference between a cluster RCT and a stepped wedge design, as I'll go on to explain in a little bit more detail. Now, within a cluster randomized controlled trial, you can have repeated measures within the same individual. So as we can see on the left here, we've got one cluster where the same subject provides 1 unit of measure, but this subject provides 2 units of measure. So perhaps if we use our primary school example, this subject might have had to have repeated the first grade, and they had a measurement conducted in this year, and the same subject had a measurement conducted the following year. You tend to get designs like this occurring in clusters where there's natural turnover of participants. So say, for example, a hospital-based randomized controlled trial of an intervention, you'll get some hospital patients that transition every time period. They come in, they're discharged, they have their measurement, and then a new person comes in, takes the same bed. But then you'll have some patients who are long-staying patients and might have multiple measurements, depending on what your outcome measure is, across the entire time period. So, for example, if the outcome measure is falls, then you'll get a measure in, say, let's say this is a calendar month of April, calendar month of May. Each subject might have a certain number of falls in April and a certain number of falls in May, yet they're all connected to being the same, related to the same individual. You can have very longitudinal studies, and you might get this in community-based cluster RCTs that take place where you're following people up for long periods of time with repeated measures. So let's say physical mobility, a timed up and go test might be the outcome measure you're looking at here. And you have a test every 3 months for the duration of the trial, and you're looking at how those measures change over time. So across cluster randomized controlled trials, there's different varieties of cross-sectional, longitudinal, and hybrid in between style follow-up approaches that can exist. And again, this is important for your analysis approaches and for considering your different design considerations. Now, there are some problems with the cluster RCT. With small numbers of clusters in particular, there is a heightened risk of confounding factors and selection bias threatening the internal validity of study findings. Basically, the clearest example that I come across is that you may not be comparing apples with apples. You may have apples with oranges, and with only a small number of fruit/clusters available to recruit, it's difficult to know if you're getting the effect of the intervention, X on Y, or whether you're getting the effect of the type of fruit you've randomly allocated into each group. Now, a debate that has come up in the falls prevention field, and those who are well familiar with the Cochrane review of falls prevention that Ian Cameron and his team led for hospitals and institutional settings, might have seen some of the correspondence that came forward back after the most recent publication. Matching of clusters means that in a particular trial, clusters are matched together based on some characteristic before they're then split into intervention and control conditions most commonly. And there was one particular trial by Dykes et al. Coming out of the United States where they used a matched approach in their design and analysis of their trial of a hospital-based falls prevention intervention. And they wrote into the authorship team of the Cochrane Review and said that to calculate the confidence interval for the rate of falls for their study in the Cochrane Review, Cameron et al. Used a formula that did not consider the effect of matching in their analyses as they used in their trial. And then they've gone on to note that in the previous publication in Statistical Science, matching greatly reduces the standard error in cluster randomized experiments. Now, in this statement, there's nothing that's inherently false. It is true that Cameron didn't use the matching approach to analysis of that trial, and that, yes, matching does greatly reduce the standard error in randomized controlled experiments. As a result, the confidence intervals of their particular trial was much wider than what they had themselves reported in their primary study. So, and even in the paper in Statistical Science, they do go through the reasoning, and they are correct in what they've said in all of those points. And I was just really wanting to make the point here in this slide that even though you can match things, it doesn't mean they're the same. It doesn't, just because statistically you can do matched analyses does not mean that you should be doing matched analyses. And in fact, from the epidemiological literature, it was first noted that matching in the design does not necessarily control for confounding by the matching factors. In fact, it can produce confounding by the matching factors even when it did not exist in the source population. So as an illustration, I actually did a trial back in my days in Queensland, back in the late thousands. And this one was a trial of low beds where we were giving out low beds. Queensland Health approached me and said, Terry, we want to give a bunch of low beds out to different hospital wards across the state. And I said, well, let's hold on how we do this. and see if we can do an experiment while we do this. And so in this particular trial, there were 18 wards that didn't previously have the low beds. And what we said was, right, what we'll do is we'll match these wards based on falls rate prior to the trial beginning. So at the beginning of the year, I asked all the hospital wards for, what are your rates of falls over the past 6 months, I think it was. And of the 18 wards, we put them into pairs based on having the highest to the lowest rates of falls. And then we split each pair at random into a control group and an intervention group. Then we measured their rates of falls for 6 months before the first tranche of beds arrived. And even with this matching, we had a significant difference in fall rates to begin with. So we used the matching approach, and we still had a significant difference in the rate of falls over the 6 months after we did the matching. So just using matching doesn't assure equivalence. And that's a really important point here. So when you look at the falls rates per 1,000 bed days, our intervention group started off having 2 falls more per 1,000 days in our control group, which as a percentage was about a 40% higher rate of falls. So other ways that we can potentially improve the cluster randomised control trial. But we can use pre-intervention commencement phase measures and also post-intervention commencement phase measures. So here with this diagram, we can see that we've got a period where we've got no intervention being provided to all the clusters, and then the intervention commences. And this allows us to use difference in difference style analyses, where you look at the difference between the time periods for the intervention clusters and compare that to the difference in time periods for the control clusters. So this is another way that you can improve the cluster randomised control trial and the equivalence in the comparisons that you're looking at. Now, with this low bed study, this is actually what we did. We had the pre-intervention period and the post-intervention period. And as you can see from the falls data here, we got a reduction in both groups. But because of that difference to begin with, our difference in difference analysis really didn't find a significant result in the rate of falls overall from this particular intervention approach. Now, in this study, we did one more thing. We eventually gave all the wards in the control group the low beds at the end of the study. At the time, we saw this as just the ethical thing to do because that was part of the conditions of entering the trial, that eventually you would get the low beds. It's just when you were getting them. Were you getting them 6 months into the year or at the end of the year? Now, if we'd taken measurements of falls in the subsequent 6-month period across all the wards, what we would have had in that trial was a stepped-wedge trial. So we'd done the first 2/3 of a stepped-wedge trial and just not the last third in that particular study. So the stepped-wedge itself is something which is very closely related to the conventional parallel cluster randomised controlled trial approach. And I'll refer people to these particular publications, one in the BMJ and one in the Journal of Physiotherapy, where Carla Hemming and I and some other authors have gone about describing the stepped-wedge trials and some variants in some key detail. So the stepped-wedge trial, what is it? It is a trial with a unidirectional crossover, normally from control to intervention, but not always. Each cluster serves as its own control. Okay, so each cluster has both control and intervention period data being created. There is an initial period in which usually all clusters are in the control condition, and subsequently, at regular intervals, or the steps as sometimes it's called, one cluster or a group of clusters is randomised to cross over from the control to the intervention condition. So it's not random allocation of getting the intervention or the control, it's random allocation of when the intervention commences. And this is sometimes referred to as a rollout design because you're rolling out the intervention to all of your clusters. And this is something that makes the stepped-wedge very popular. I sit on the NHMRC partnership panel I sat on a couple of panels for them last year, and it was very common to see people saying, this is an intervention rollout design which supports implementation and evaluation of an implementation of an intervention. This process continues until all the clusters have crossed over from one condition to the other. The last period has all the clusters usually in the intervention condition, and the data collection continues throughout the study. So it is a resource-intensive research approach if your data collection is not routine. So this is why you'll see these designs quite commonly in hospitals and aged care facilities where there's routine collection of falls-based data. Now, some of the key differences here, the Stepped-Wedge has better control for confounding and selection bias, particularly if the number of clusters is low, because each cluster is serving as their own control. Because everyone gets the intervention eventually, I find it much easier to convince service providers to participate in a trial if it is of the Stepped-Wedge design, rather than if there's a 50-50 chance of getting the control condition. The Stepped-Wedge cluster size requirements are likely, not always, but likely to be lower than for a parallel cluster RCT. The data collection burden can be higher, as I've mentioned, unless routinely collected data is being used. The Stepped-Wedge has to statistically adjust for the confounding of time. And if anyone is ever reviewing a Stepped-Wedge trial, it's important to pay particular attention to the analysis approach and that they are adjusting for the confounding effects of time, because it is not something that I see that authors are routinely doing, despite recommendations to do so. The other issue is that the Stepped-Wedge is bound to deliver the intervention on schedule. So when I showed you the picture of the parallel cluster RCT with, I guess, the staggered commencement times, you don't have that option available in the Stepped-Wedge. You need to try and commence the intervention when it is scheduled to commence at each ward. And that is a key restriction that sometimes makes Stepped-Wedge more difficult to run. So in terms of the evidence hierarchy, where does the Stepped-Wedge sit in relation to the cluster RCT? Well, I would argue that it sits alongside it. There's a couple of lines of argument for this, but for one of these lines of argument, I observed that hidden within a Stepped-Wedge trial is a parallel cluster randomised trial. So if you look at the red cells hidden here, you can see that there has been a random allocation process. There is the ability to pick parallel wards with the same exposure to time period. And if you look at how this particular design can be mapped, you can actually get just under half of the same data you collect in a Stepped-Wedge design, extract it and use it as a parallel cluster RCT analysis from the same study. And if ever I get time, I'll go through a whole bunch of Stepped-Wedge studies and see if there is any systematic bias in the results when you analyse data this way compared to analysing it as a Stepped-Wedge. But that's one of the many things on my long list of things that Terry will eventually get around to, but probably never will. One of the things I will raise as well that's very important is that summative data and meta-analysis from a Stepped-Wedge do not go together. Let me show you why. Here we have a mock trial whereby, let's say this is a number of falls on an aged care facility. There's 6 aged care facility clusters and 7 time periods over which the observations have been taken. The intervention here has reduced the average number of falls in each cluster by 2. So the control mean is 9.2 falls per time period. The intervention mean is 4.1 falls per time period. I'll also point out the heterogeneity here. The cluster 6 has a much higher number of falls than all the other clusters. What would happen to those summary statistics, though, if by random allocation, cluster 6 had been moved to cluster 1? Well, I've done that here. And all the data is the same in terms of what the rate of falls is for each cluster, and that there has been a 2-fall reduction per cluster as a result of the intervention. But you can see that the mean is now very different for the control and the intervention group. So just taking the summative scores of mean and standard deviation from a stepped-wedge trial can be very misleading as to whether the intervention has had an effect or not. So you must pay attention to that when both reviewing a stepped-wedge trial and when using stepped-wedge data in a meta-analysis. What we should be using is the effect sizes and the 95% confidence intervals from analyses that adjust for the time period. That's the key information that we need to be paying attention to. With presenting data from a stepped-wedge trial, here's some data from a trial that I've run previously, where I've tried to summarise the number of falls, the number of fallers, the number of falls with injury, the number of falls with hospital transfer, and the number of patient days of observation. It gets a bit messy when you present data this way. So summative data has limitations, but also presenting data in this way can be a little bit unuseful. So in the paper that I referred to you before in the Journal of Physiotherapy, but also in this paper here, which Joe Gellett led, looking at removal of falls risk screening tools from hospital wards, there's a few different ways you can present data from a stepped-wedge trial. So in this stepped-wedge trial, we've got the proportion of people who fell in hospital measured over different calendar months. The problem with this approach is you don't quite see where the intervention started for each ward. This is a stepped-wedge trial. What you can do is separate those time periods for the control and intervention period. What you lose by separating those is those time-based fluctuations, which we adjust for statistically. So one of the proposals I put in that Journal of Physiotherapy paper is that we should be presenting data in a time to transition relative line graph form. So the blue line that goes down the middle of this graph is the transition time point for every cluster in a stepped wedge, and that some clusters have more time before the transition and others have less time. But this allows you to see what happens straight after the transition. The thing you lose here, though, is the effect of time, And, fall rates sometimes go up and down over different calendar months. So you've lost that here. So the final approach, and this is what we put in Joe Gellett's paper, is to look at a residuals graph. So we ran a regression where we adjusted for the effect of time, collected the residuals from the analysis and plotted those residuals. And it's where you see those residuals in the bottom right-hand corner here that you start to see that, actually in the intervention period after the transition in this study, the rates of falls actually did go down a bit, from a visual analysis perspective. So just quickly, there are some variations of the stepped wedge design that's important to be aware of. The Alan Girling hybrid method. Alan Girling was a statistician who used to work with Carla Hemming at the University of Birmingham in the UK before he retired. Took me out for a wonderful Indian meal at one stage when I went over there to visit them. And he proposed having one group of clusters that were entirely intervention and one group of clusters that were entirely control for the study period. And he found that that increased the statistical power and reduced your sample size requirements for some of the simulations that he modeled. There is also the staircase design, which is a form of incomplete stepped wedge. I haven't used a staircase design before, but there's a couple of variations. I don't know if I'm fully on board with the staircase design because in a stepped wedge design, each cell in the design actually doesn't contribute the same amount of influence to the overall result. It's actually the cells either side of the transition and the cells in the far extreme corners that contribute, have a greater influence on the effect sized estimates. So by removing those corner cells from the design, you actually lose a bit of statistical power using the staircase design. You can have stepped wedge designs with randomisation of individuals instead of clusters. So this is a trial that I've been a part of where we've looked at the timing of commencement of a lifestyle intervention for people with CPAP, intervention for obstructive sleep apnea. And what we wanted to see was, did delaying the start of this lifestyle intervention have a bigger effect on these people's weight loss and obstructive sleep apnea hypoxia index scores? And in this design, we had a standard stepped wedge where everyone got the lifestyle intervention. People all started CPAP at the start of the design. And we would follow them up for 6 months for the stepped wedge. But we also continued that on for an extended period of time. And therefore, we could do an analysis in a few different ways. We had that initial stepped wedge analysis. We had the overall results at 12 months and the overall results at the end of the 6-month lifestyle intervention period for every participant as well. So it created a few different ways that we could slice that up, which was very interesting. Another design that you'll see sometimes emerging in the literature is the disinvestment stepped wedge. So this is where we turned the stepped wedge on its head and said, right, we've got a part of usual practice, a part of usual care, which we're concerned may be ineffective or it may be inefficient. And we want to see what happens if we remove that aspect of usual care. So the conventional stepped wedge, we transition from control to intervention, but in the disinvestment stepped wedge, we transition from an intervention provision condition to a no intervention condition control. Now, in this particular trial, we completed this one, first of all, looking at removal of weekend allied health services, medical and surgical wards across a number of hospitals in Victoria. And we did have 2 phases. We had an initial disinvestment from the weekend allied health service. We redesigned them during the second control period and then re-implemented them in a different form in this black period down here. So we actually had 2 trials in sequence. We had 3 conditions in each trial, and it created a few headaches for us because our 2 control conditions we found weren't equivalent to each other. When we statistically compared this period of control to that period of control, they were different on a number of outcomes, which is something we hadn't anticipated. The other thing was that one of the wards closed, which for a stepped wedge trial is a limitation, that it does take a while to get these trials done, and the longer you go for, the more risk that something's going to happen to one of your clusters. Now, as a way to deal with that issue, I dreamt up a new way of doing the disinvestment stepped wedge, which was instead of in parallel, was a concurrent design. So here you see on screen a 3-group stepped wedge design. We've just had the protocol paper published. In this trial, what we're going to be doing is be comparing rates of falls on hospital wards with high levels of use of bed alarms, and we're going to transition them to either having no bed alarms at all or a moderate level of bed alarms, so a reduced level but not completely eliminated. And I'm very interested in this question because previous research looking at bed alarms is starting to indicate that bed alarms are ineffective or may even be harmful. But the control conditions in the bed alarms research hasn't looked at an eliminated condition. Quite often there's been some low level of bed alarms being used, some but not completely eliminated. So I thought it was very important to have a look at this particular question, and we'll be using this 3-group disinvestment design to address that question. You could extend this to a 4-group design, a 5-group, 6-group design as a form of conducting a stepped wedge, depending on how many groups or how many levels of intervention or control are of interest to you and your team. And I might leave this presentation at that in case there's time for a couple of quick questions. So I'll stop sharing the screen. Does anyone have any quick questions that we can fit in?
Okay.
Terry, oh, no.
Sorry, you go, Kathy.
No, I was just going to say, Terry, I was just texting Charlotte and suggesting that we perhaps have a further session, because I imagine people have got meetings at 1 o'clock. But yeah, I think it'd be great to, hear more from you in a more relaxed manner, as well as have some time for discussion, because I think there's a wealth of expertise there that we can really benefit from multiple studies.
Indeed. Happy to reconvene at a later time and discuss these issues. When it comes to research design, that there's nothing that's quite set in stone, and being able to look at all the different variations and ways you can manipulate things a little bit differently is a passion area of mine. So more than happy to have a chat about this in future.
Fantastic. I did have one quick question, unless anyone else does. I was interested in the implications for meta-analysis, Terry. So currently with Cochrane reviews, there's very strict ways about the way they're done. So are you saying that stepped-wedge trials can't really be incorporated at the moment?
No, you have to use the effect size estimates from what would be either a linear mixed model or a generalized estimating equation. You should not be using summative data of just the raw characteristics of the outcome measure summarised across the groups. As I indicated in the example, heterogeneity in those figures can lead to very misleading results.
Mm-hmm. Thank you.
And can I just ask a question? And it's a dumb question, but I'm happy to ask those types.
There's no dumb questions.
So Terry, I'm just trying to get my head around so it's effectively like a pre-post design, but you're randomizing the stepping.
Yes, so, it's randomly allocated when a group gets an intervention.
How does that overcome bias? Like I'm trying to get my head around how it overcomes bias just by changing the time when people start.
Yeah, the counterfactual that you have here is drawn from the control period data. So what you're supposing is that, right, we've got two concurrent effects happening here. One is a time-based effect of natural change over time, maturation or natural healing that might take place, or decline in the case of following up individuals over a long period of time. And that your control period data is allowing that to be modelled. Yep. Okay, so that bottom corner of the wedge allows those biases to be modelled in the analysis approach. So it's combining both a design and an analytic strategy. Again, without the analysis that adjusts for those time-based effects, the stepped wedge will give you a biased estimate of the treatment effect. But the difference between the stepped wedge and other pre-post-based studies is the ability to account for natural maturation or decline or time-based variations in the outcome measure.
If we talk about health services, there might be changes intrinsically within the health service.
Yeah. And one of the biggest changes that I've ever seen in falls rates in a health service came about when a health service transitioned from paper-based to electronic medical records. And there was a massive drop in falls. Now, if that happened in the middle of a stepped wedge, that would actually be fine, because that would be incorporated into the time-based impact in your analysis model.
Okay, great. Yes, that makes sense now.
Sounds like a novel approach to solving falls in hospitals, Terry.
just create very difficult ways for people to report them and transition onto them. Yes.
You want something to work, change the system.
Brilliant. Well, that is 1:02, so we will let everyone get on with their day. But thank you so much, Terry, and apologies to Terry and everyone for the session being a little more eventful than we had planned for. But as Kathy said, we'll follow up with another session, hopefully, where there's less interruptions. But that was brilliant and lots for everyone to think about, I'm sure. So I hope everyone has a great rest of your day, and we'll be in touch, I'm sure, at various points. Sandra will be in touch with more details of the next seminar too. Bye all.
See you later, everyone.
Excellent. Thanks again, Terry.